Hi everybody, welcome back. We are returning to our cliffhanger where we left off at the end of the last video. So we had just discussed how the sidereal day, which is the time that it takes Earth to rotate exactly once, is a little bit less than 24 hours. It's about 23 hours and 56 minutes. So the stars rise 4 minutes earlier every day. Sidereal means with respect to the stars, and our actual rotation period is a little less than 24 hours by about 4 minutes. So we left off with the question, what if Earth rotated in a direction that was opposite from its orbital direction? In other words, if Earth rotated, say, from east to west, such that the sun rose in the west instead in the east, would the solar day still be longer than the sidereal day? Remember, the solar day is that 24-hour day, the average time between high noons. So hopefully you've had a chance to think about that, and the answer is that in that case the solar day would end up being shorter, because just going back to our kind of zooming in with the situation, remember the reason the solar day is longer than the sidereal day is because as Earth revolves around the sun, it's rotating, and it's the rotation that brings into being the days. But yeah, as we're rotating, we're revolving around the sun. So as we move around the sun, we have to rotate a little bit extra to get the sun in the same part of the sky, which is the time for solar days, how long it takes for the sun to be in the same part of the sky from day to day. But if Earth was rotating in the opposite direction as it orbits, for example, if it was rotating clockwise, well, during the time that Earth moved in its orbit, it would not have to rotate as much before a particular point on Earth got back into view with the sun being directly overhead. So in that case, if Earth was rotating opposite the direction of orbiting, opposite its revolution, that is, then the solar day would end up being shorter than the sidereal day. And that is indeed the case on the planet Venus. In fact, on Venus, the solar day is a lot shorter than the sidereal day because Venus has a very slow rotation that is retrograde. Now, so as we mentioned, the solar day is longer than the sidereal day by about 4 minutes. However, the length of the apparent day is actually a variable. The reason for this is because Earth's orbit is not a perfect circle. So there are some times during our orbit where we don't quite have to rotate as much extra in order to get the sun in the same part of the sky again. And there are other times during our orbit when we have to rotate even more so. And the times where we have to rotate more than we otherwise would to get the sun in the same part of the sky again are the times when we are closest to the sun in our orbit, because for reasons that we're going to discuss in a couple of units, that is, well, actually in the next unit, that is when Earth is moving fastest in its orbit around the sun. So because of this, we say that the 24 hours is the mean solar day. It's the average length of the solar day. But if you were to plot the position of our sun at high noon, so to speak, or what we think of as high noon according to our watches, it would have its position in the sky would change from day to day, not just because of the tilt of Earth's axis, but also because of that difference with Earth rotating a little bit extra when it's needing to rotate a little bit extra when it's close to the sun, and a little bit not as much extra when it's farther away from the sun. It always rotates a little bit extra to get the sun in the same part of the sky, but there are some days where it rotates more extra and some days where it rotates less extra. So sundials help us to kind of keep this mean solar time, but yeah, if you're to plot the actual position of the sun, then things are going to be a little bit different from day to day. So, as a result, you get a figure called an analemma. An analemma. And this is an analemma. It's kind of a nice figure 8 pattern. And this is what you get when you plot our sun's position in the sky at 12 o'clock each day. Well, in this case, it's like every 3 or 4 days. But still, if you do that over the course of a year, you get this kind of figure 8. However, this is again, kind of just going back a couple of slides, a result of Kepler's second law, the fact that Earth moves faster when it's closer to the Sun, which is in January, and it moves slower when it's farther from the Sun in July. So when it's closer to the Sun, it has to rotate a little bit extra. Now, if Earth had a perfectly circular orbit, then instead of having a figure 8 pattern, it would just end up being a vertical line. It would just be a vertical line. So that's something to kind of keep in mind. And here is kind of just a plot of the analemma as a function of date. Now, more about timekeeping. As you know, well, Earth rotates, so it would be nonsensical to have just one time zone for the whole world, because otherwise people would be getting up for their day at 3 p.m. or stuff like that. So we generally think of certain times of day as being the times when we wake up, certain times as the times when we go to bed. So this didn't really used to be all that much of an issue for people. People just kind of kept local time. But once the Transcontinental Railroad ended up really linking cities throughout the United States, it became necessary to establish time zones. So finally, in 1883, the Transcontinental Railroad was completed in the late 1870s, but in 1883, the railroad companies divided the United States into 4 time zones. Alaska was not part of the Transcontinental Railroad, and obviously Hawaii wasn't either. So because of this, we ended up with 4 time zones. And eventually these types of time zones, or at least the philosophy of these time zones, was taken up by other countries, such that now we have an international date line that officially divides one day from the other, and an establishment of a whole bunch of time zones across the world. Now, this isn't completely current. For example, I know that Venezuela kind of does weird things with their time zones all the time. North Korea, I think, has a weird time zone. And some of the African countries are like plus or minus 15 minutes from other people and stuff like that. But overall, there is a general trend such that when you go 15 degrees longitude east, you increase by 1 hour on average. And 15 degrees longitude west, you decrease by 1 hour. But then when you cross the international date line, boom, you're on the next day. So again, notice the United States, Eastern Standard Time is in purple. And then you also have Atlantic Standard Time, which is in yellow here. And that's where you're dealing with like Nova Scotia and everything. I once went on a cruise to Nova Scotia, and they were on Atlantic Standard Time. That was kind of interesting, except it didn't really matter because they don't do daylight saving time. So since the cruise was in the summer, it was actually the same as Eastern Standard Time at that time. Okay. Speaking of daylight saving time, since 2007, the United States has had our clock set ahead 1 hour on the second Sunday in March, and you fall back to normal time on the first Sunday in November. Before that, it happened like, I think about 2 weeks previous to that, like the second to last Sunday in October, and then they went a little bit later before they set them ahead in March. So either way, the idea is spring ahead, fall back. And daylight saving time begins when you spring your clocks ahead, and then it returns to normal time when you return your clocks back in the fall, when you fall back. Now, not all states participate in this, so that's something else to keep in mind. Most states in the United States do participate in this, but I believe Arizona does not participate, and I think there's one other state that doesn't participate in this as well. And as far as I know, I think most countries don't participate in daylight saving time, but most European countries do. Now, we've talked about precession already. Precession has an effect not just on the precession of the equinoxes, so to speak, and the fact that your zodiac signs are off by a month, and the fact that Ophiuchus has crept into the zodiac. Precession also has an effect on the length of the year, and it's quite interesting. So just a reminder, whenever you have an object that is rotating and you exert a force on that rotating object, if the direction of that force is not down the axis of rotation, the result is that there will end up being a net torque on the whole object such that the axis of rotation ends up moving around. And this is exactly what happens with Earth. Now, the effect itself was discovered by none other than Hipparchus. Hipparchus is the same ancient Greek astronomer who invented the stellar magnitude system. But it causes the north and south celestial poles to move through the sky. We saw that in a previous video. So, as time goes on, the Earth's geographic pole ends up changing. This has nothing to do with the magnetic pole moving and stuff like that, which happens over the course of years to decades. The fact that the direction that the north geographic pole points in space changes over a period of 26,000 years, or at least it completes a whole loop over a period of 26,000 years. So this is not to say that the actual spot of Earth's axis of rotation changes. That does not actually happen. The north geographic pole is always in the same spot. It's just that the direction that is the point in the sky that's directly overhead from the north geographic pole, that changes over a very long time scale, over 26,000 years. So a result of this is the so-called precession of the equinoxes. We've already talked about the fact that the zodiac constellations have shifted by a month since the ancient Greeks established them over 2,000 years ago. But also the point where our sun crosses the celestial equator from south to north, that is the location of the vernal equinox, that also changes over time. Right now it's in Pisces. About 2,500 years ago it was in the constellation Aries. And 4,000 years ago, it was in Taurus, and the bull associated with fertility, which, that mnemonic kind of worked for them in terms of thinking about, okay, the vernal equinox happens in Taurus. Well, in 2700 AD, the vernal equinox will actually be in the constellation Aquarius, and that will truly be the age of Aquarius. So this is where you would be cued to do a YouTube search for the song Age of Aquarius. So, in other words, as Earth's axis precesses, the celestial equator also precesses with respect to the ecliptic, because the celestial equator is just above Earth's equator, and as the direction, so it's like right now as Earth rotates and goes around the sun, the North Pole will always be pointed toward this certain spot in the sky, at least over the coming years and decades. But over the centuries and millennia, that is slowly going to move into other spots, and as that happens, the whole celestial equator is going to move, it's going to the plane is going to shift. The plane is going to shift, which means the location of the vernal equinox is going to shift. So that's why that happens. This also has an effect on the length of the year. What is a year? Well, it depends who you ask. It depends on what the definition is, in other words. A sidereal year is the time that it takes Earth to complete exactly one orbit. It's about 365.26 days. However, that is not our calendar year. Our calendar year is the tropical year, which is the time that it takes our sun to go from one vernal equinox to another. And the fact that there is that difference is due to precession. It's due to that precession that we were talking about here, where the direction that Earth's axis of rotation points ends up changing, and as a result, the orientation of the celestial equator with respect to the ecliptic changes. There's always going to be about a 23-degree tilt there, but where that 23-degree tilt is, in other words, the position where the celestial equator ends up hitting the ecliptic, is going to change over the course of centuries. And again, this was first discovered by Hipparchus, who noted that star maps that were created during the time of Aristotle weren't right anymore. They were off. So, in any case, our calendars are based on the tropical year, which is the time to go from vernal equinox to vernal equinox. That's 365.24 days. And again, that's where we end up getting our calendars. Now, interestingly, while we're on the subject of calendars, why do we have leap years? Well, how does it work? Well, the year isn't exactly 365 days. The year is closer to 365 and a quarter days. So what that means is that if you were to ignore leap years, then after 4 years, that would mean that that another day has passed that you have not really taken into consideration. So you need to take that into consideration by adding another day on the calendar. So the actual, or more, probably a better way of thinking of it is if you pretend that the year is 365 days, well, after 4 years, then Earth is a day behind in its revolution around the sun in order to get back to the same point in its orbit. So, or at least to get back to the vernal equinox again. So you need to add another day in the calendar to wait for the vernal equinox to occur again. So this was known back in ancient times. It was known back during the times of the ancient Greeks, and certainly during the times of the Romans. That's where the Julian calendar comes from, Julius Caesar. The idea being that they recognize that, yeah, every 4 years you need to add a day. Well, it turned out that that wasn't quite right. The year isn't exactly 365 days and a quarter days. It's more like 365.24 days. Well, what that means is that if you apply the previous prescription, every 100 years, you will have actually used an extra day that you weren't supposed to use. In other words, Earth will be ahead of where it should be compared with the vernal equinox, and you need to get rid of a day from your calendar. Well, they didn't realize this for a while until, and the remedy was the Gregorian calendar, which was imposed by Pope Gregory I, aka Pope Gregory the Great. And one of the results of this is that suddenly 2 weeks just disappeared when they tried to, because they wanted to return the situation back to how it was in ancient times with the seasons happening at a certain time. So with the Gregorian calendar, this took into account the fact that, yeah, every 100 years you need to get rid of a day. So the way you do that is where you would have had a February 29th, you don't celebrate it. So in the year 1800, they didn't celebrate February 29th, they didn't have a February 29th. In the year 1900, they didn't have a February 29th. But other than that, you have a February 29th every 4 years. So every year that's a multiple of 4, unless the year is a multiple of 100. Well, here's the thing. The length of the year is not exactly 365.24 days. It's actually closer to 365.242 days. So as a result, that would mean that if we were to apply the previous prescription, every 500 years, you would end up needing to add a February 29th or an extra day when you would not normally do that. Because remember, you don't do it on years that are multiples of 100. But now we're saying that years that are multiples of 500, you need to do that. That's why the year 2000 actually did have a February 29th. But wait, there's more. Yes, there's always more when you're dealing with irrational numbers. There's always more. The length of the year is not exactly 365.242 days. It's actually closer to about 365.2422 days, which would mean that in addition to adding a February 29th when you normally would not every 500 years, you would also need to add an extra day every 5,000 years, such that every 5,000 years you would have a February 30th. And wouldn't it really suck to be born on that day? Luckily, Pope Gregory the Great, or at least his advisors, realized this problem and decided not to do it that way. Instead, they don't have the extra leap year every 500 years. They actually have it every 400 years. And then corrections from that are made as needed. So anyway, that is the rest of what concerns us for timekeeping and seasons and stuff like that. So before the next video, I'm going to leave you hanging on something to consider. This word, it's an awesome word, syzygy. Check it out. 6 letters, 3 syllables, and, quote, no traditional vowels. Syzygy. So consider, what do you think this means? And what might this have to do with eclipses? So think about that, and I'll see you then. Thank you for watching.